Somebody give me the go sign.
Now.
All right. Hey, welcome everybody. Thanks for attending our Opus IVS webinar series. My name is Eric Sharping, and I'm here to introduce to you Chris Martino. Many of you all know Chris. He's been working in the industry since '98. Had his own shop for 5 years, and then branched out and just worked at Independence, doing diagnostics and refining his diagnostic skills. As a founding member of Trained by Techs, and does the tech support on the VAG desk, as well as a couple other things for Opus IVS with regard to ADOS and whatnot. He's also a WorldPack training instructor for Volkswagen, and he has a passion for diagnostics and especially scopes. So that's what we're going to be talking about today. I'm going to turn it over to Chris here in just a moment. But before I do, because of this focus on oscilloscopes, Opus has in the past had an affiliation with one scope or another. And our current agreement and affiliation has moved over to Pico. So as many of you may not know, but now you do, we also distribute the Pico Scope. The 4425 is the model that we're distributing right now, and we'd like to make a special offer for this series only, 25% off a Pico Scope with the purchase of a DrivePro ES. That's our newest DrivePro platform, which was discussed at the last webinar. So if you missed that, jump on our YouTube channel and check that out. We got 0%, zero money down, no payments for 90 days on the DrivePro ES. We'll ship you the starter kit for the Pico, which comes with everything you're going to need to start, including the coilover plug wand, which I think is kind of interesting and neat that they're still adding that in there as part of the kit. Pretty cool. What do you get with the DrivePro ES? Well, you get software updates for a year, tech support from licensed, from brand specific experts. We have over 100 plus master techs working for Opus IVS. We get licensed OE diagnostic software for many of the models, and built-in remote flash programming for also for many models. Depending on what you're working with, we may have it covered right there on the tool. So again, if you're thinking about purchasing a DrivePro ES, this is the perfect time. 25% off the scope as well. All right. That said, I'm gonna turn this over to Chris. He's gonna start this presentation, and I'll probably jump in at the end and push this offer one more time. All right, over to you, Chris.
Thanks, Eric. How you doing, guys? Eric introduced me, so I need no further introduction. He did such a great job at that. Today we're going to cover LabScope Basics. I call this LabScope Basics 101. We got a lot to get through today, so let's get started. All right, so what is a LabScope? Okay, a LabScope is essentially a multimeter on steroids. Okay, generally on the help desk, when I talk to people about using an oscilloscope or a LabScope, they always ask me, can I use a multimeter? Most multimeters refresh around every 250 milliseconds. Some are faster, some are slower, but that's usually a good refresh rate. Meters will usually display the average of the measurements within that time period. So if voltage goes up or down with every 250 milliseconds, you're generally going to see a steady of voltage. Most multimeters will not allow you to save and play back your measurements for analysis. Vehicle modules read data hundreds to thousands of times faster than any scan tool or multimeter. And this is coming from a guy that works for a scan tool company. Okay, there is no scan tool out there that can read as fast as a computer reads. Data is great, but there are times when data lies to you, and you need to see what the sensor tells you. All right, multimeters have their place, but to really get in and see what a vehicle does, or a sensor does, or a system does, you need to look at that with an oscilloscope. So people generally ask the next question: what about min-max mode? And for those of you who don't know, when on meters, when you use min-max, it'll effectively up your sample rate of a multimeter. Okay, that is better than a normal a multimeter, but not the best. Let me show you why. Okay, we have a 2000 Range Rover 4.6. I did this myself about 50 pounds ago at the shop. It was one of the last cars I worked on when I was there. The problem with this one was the ABS light was on. Not only was the ABS light on, when you drive the car from about 15 to 30 miles an hour, the whole dash would light up like a Christmas tree. The brake pedal would go crazy, and you would lose communication to the ABS control module. All right. So since we're dealing with a communication issue, the first thing you want to do is see how everything communicates. And this particular vehicle right here communicates on this pink wire right here, which goes up to this pin 7. Okay, communicates on a K bus. Okay, so now we know how the module communicates. So all these modules here are all put together. So now that we know how the module communicates, we need to know what it takes to have a module work. It's pretty simple. You need power, ground, some form of communication. That's it to make a module work. So we go to a wiring diagram and we check power, ground, and communication. All right. I want to know when I'm driving, what am I losing? Why is this module freaking out? Basically, why is it dropping communication? And then when I get out and get back in, it starts to communicate. So I want to make sure that I'm not losing power. So I'm going to check in power right over here. I'm going to check my ground right over here. And I also want to look at my K-line communication, but I also want to look at some kind of output from this module. In this particular case, I'm going to be over here from a speed sensor signal that the module outputs to the body control module, into the cluster, stuff like that, so the car actually knows how fast it's going. All right, so I hook all that up, and I got something that looks like this. Okay, so what we have on top, on our blue trace, right over there, we have our power from our fuse. It's at 12 volts or system voltage. All right, this green right here, that's the actual communication. All right, that's the K-line communication. We're going to get into that in a little bit. All right, this red, this is the actual output from the signal that's going to all the other modules for like a speed signal or whatever. And we also have our ground down here all the way at the bottom. Now, why do we check a ground? Well, it's kind of important because a lot of people neglect the ground side of diagnostics. They'll check power all day long. They'll put a power probe in there, which is always great, or they'll use a test light to check for power. And oh yeah, I got 12 volts. It's no big deal. If you don't have ground, it's just as bad as not having power. So generally, what we're looking for on a ground side is around 0 to 100 millivolts. Something close to 0. If we see voltage rising on the ground side, that means we have a voltage drop, or we have some kind of resistance to ground. And like I said, again, the module doesn't have enough effective voltage to work. All right, and we want all this to remain steady while we're testing it. So this is what it looks like when we first hook to the car and everything's working just fine. We start driving the car. Well, actually, no. I wanted to go, and this right here is what good K-line communication looks like. It's basically it's a bunch of little square waves, almost like a LIN bus kind of. But you can see the packet, the data, the module's talking, modules are responding. Everything's good and healthy. So we drive the car, okay? And one of the couple things that we notice is while we're driving the car, our power stays at 12 volts. Our ground stays close to 0. All right. We're looking at these packets right here. We see some data here. There's something going on over there. Oh boy, something's over here. This is okay. And then it just goes away. All right. You see these little guys right over there. I call that the knock-knock signal. All right, the way K-line generally works is you get a master module or a scan tool of some sort, basically saying knock knock, is anybody home? And the modules will respond. The modules will generally respond with, yeah, we're here. So what's going on is a master module or the scan tool is going knock knock, and nobody's home. Communication is dropped out. All right. So what do we see at this capture? We do see that we're not losing 12 volts while we lose communication. We are also not losing ground. We know power and ground isn't an issue. But we can also see on this communication line, all of a sudden we have a square wave happening. Okay. What is this square wave? Personally, I don't care. All right, I just want to know if something is working. What we might theorize is maybe this is the substituted data coming from the other modules or coming from the vehicle speed sensor, so the car can still do its functions that it needs to see vehicle speed to do. I personally don't care. It just tells me that that module is working or something is working. It's responding. We're not losing the rest of the car. All right. So I know this is fine. I want to move on from there. Okay. So I know that this is happening while the vehicle is moving. So what else could make a module freak out while the vehicle is moving? I want to check wheel speed sensors. Okay. So I wanted to check all 4 wheel speed sensors. I'm not going to bore you by giving you all 4. I wanted to show you this capture right here. I changed the background so to make it easier to see. Okay. And what you can kind of see here is you can kind of see basically the sine wave. This is where I wanted to get back to what we were talking about with, can I use min-max mode or can I use a multimeter to check this? Well, when we first used multimeters to check speed sensors, basically you put your positive and negative up to the wheel speed sensor and spin it. If you got a voltage, it's doing stuff. Then what you do is you go to the next wheel, spin it, hopefully the same speed, hopefully you're torquing it the right way with the arm and the caliper's not locked up and it's the same voltage. And you do that for all 4. Cool, we got voltage. I can guarantee you, I go to this particular wheel and I put my multimeter on it and it spins just fine. And it's the same voltage as all the other wheels. Okay. Even in min-max mode, it'll be the same. Okay. But what I do notice is that we have all these little dropouts happening on this. Okay. And you can also see that they're happening all about the same spot or the same time in the revolution. And if you count them, you'll see they're happening at the same time. All right, let's go back to the 250 milliseconds of a multimeter. All right, what I did basically here is I took 250 milliseconds and basically split it up on the screen. So we have 250 milliseconds here, 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 and here. So what your multimeter is doing is it's sampling here, sampling here, sampling here, and sampling here. And saying, okay, we got about 6 volts here, 6 volts here, 6 volts here, 6 volts here. We have 6 volts going on this sensor. I'm just making numbers up, but that's basically what's going on. That sensor's working. So if you had an ABS sensor code, let's say, and you did this test, all right, and you did it with a multimeter, you'd put a sensor in the car and it would come right back. So then what you'd do is you'd go and put another sensor in the car, all right, and the code will come back. And then what you would do is you go to the dealer and get another sensor for the car. That wouldn't work. So then what you would do is you go to a junkyard, get one that you know that works, put it in the car, and then it won't work, and then you're fired. And then you got to find another job. But what do we see? Let's do this smartly. We're using a scope now, all right, to see the actual voltage, and we see these repetitive dropouts that are going on this wheel, and it's happening at the same time. Okay. So, and it's also happening like 7.9 milliseconds. Is the length of a dropout, which a meter can't even read. Okay, so let's go over this. This vehicle has a repetitive dropout that happens during each revolution. The only thing this could be is the ABS ring. That's it. It could, because if you have now imagine you have a missing tooth on your ABS ring. All right, you got your up and downs. Then if you have a missing tooth, it's going to be missing. That's going to go up and down again. That's exactly what we got going on over here. So this car needed an axle, and it was done. We drove the car, and the ABS worked. Nothing freaked out. I mean, it was a 2000 Land Rover, so it still was a load of garbage, but everything was fine from there. Cool. So let's go back. So why do we use a lab scope? We want to view data that happens too fast for us to see. And as diagnosticians, proper and effective diagnosis requires us to see and interpret information as fast as a computer receives it. You may think that is a no-brainer, but you really need to see a scope. And like I said, scan tools generally for a lot of signals are too slow. And sometimes, like in this particular vehicle, the problem happened too fast. There is no scan tool in the world that's saying that's going to have a missed tooth. All right. Scan tools lab scopes also allow us to record and sync data to identify when and where problems can be. Okay, we're going to go over that in a minute. Vehicle modules read hundreds to thousands of times faster than any scan tool or multimeter. All right, so let's move on. Our next car here is a 2006 Audi A4. This is a 2.0 liter BPG engine, excuse me. The code we have here is a P0321 with engine speed sensor plausibility. Let's talk a little bit about this engine real quick because I put the code up there for a reason. This 2-liter BPG is a direct injected Volkswagen Audi motor. And it's one of the first generations of it, where it was like the older 1.8Ts. That's basically the block is based off of that, where it has a timing belt in the front and then a timing chain in the back of the car that runs the cams. All right, so that's what we want to go with that. But we have a code here for the P0321 engine speed sensor plausibility. All right, this particular call was a tech support call. Okay, and the guy that I spoke to, he was about the third guy in. It's had timing belts, it's had cam sensors, it's had crank sensors. They were about to do a harness. They wanted to condemn the computer. I said, oh, hold on a second, let's stop. Do you have a lab scope? And he goes, no. I was like, fine, you don't have a lab scope, okay. Do you have a snap-on tool? And he said, yes, I do. I said, what kind of tool? He goes, I have a Varus. I was like, awesome, you have a lab scope. Let me log into that. Wait, you can log into my lab scope? Yes, yes, I can. That's what I do here. So after proceeding to log into his lab scope, we took a look. But let's go a little bit further. All right, before I'm going that crazy, you want to look a lot of steps that are overlooked on diagnostics is actually looking at the malfunction criteria. You can see this is pulled right from all data. All right, you see a P0321, and it's basically an ignition, distributor, engine speed, performance. It's basically saying cam crank sensors don't match. All right, the diagnostic procedure that I want you to check if you want to go and look at a trouble tree, which I advise you don't. Want you to check the engine speed sensor, and it says refer to engine coolant temperature sensor checking. And I can guarantee you, if you click that link, it'll let you go to the engine coolant sensor checking page, but there's nothing there about checking a crank sensor, which is G28. It's there for some factory reason. Don't know why, but we don't care. But this is the most important part right here. All right. The malfunction criteria and threshold value. Your counted versus reference teeth is more than one. Basically, it's saying where the cam and crank sensor meet, they're supposed to meet at a certain spot. And if it's more than one tooth off of your reluctor ring, bless you, Gina. There's more than one tooth off of your reluctor ring, it's going to set a code. Awesome. So we know we've got a cam crank correlation issue. Cool. So we also happens around 600 to 1600 RPM, low idle to low ride, and between less than 1 or 15 miles an hour. Cool. So now we know how to check this. So now this is when I tell the guy, let's hook up a lab scope. Okay. So we go in, I log in, then we hook to his cam sensor and crank sensor. Okay. Well, here, let's do this again. So how do we check this? You can replace the crank sensor and hope for the best. No. You can check the timing belt marks. No, that's too much time. You take stuff apart until we get lucky. No. The name of the game is to take as little apart and get the most information possible. I'm fat and lazy. I don't want to do much work. I want to get in and get out. All right, so we're going to check. We're going to go to our engine RPM sensor, which is our crank sensor. We're going to go to our cam sensor. Okay, awesome. Now we've got a diagram like this. All right, we want to check to our signal wire coming out of our cam sensor. What do? There's nothing here. Well, let's make it a little bit easier. All right, see those two wires there? They're shared between the fuel pressure sensor and the cam sensor. Okay, those two wires are shared. There's no way that can be a signal return. That only leaves that little guy right there. That's our signal wire. That's what we're going to hook our scope up to. Okay. We're also going to hook to that wire of the crank sensor. This is a 2-wire crank sensor with this little shield. That little wire, that's the shield right there. All right. That we're not going to hook to that. It doesn't matter on a 2-wire crank sensor where you're going to hook up to. The pattern will be upside down or right side up or upside down. It doesn't matter. It's going to be in the same relation. So we're just going to pick that gray wire right there. And this is what we get. Okay. Now you can see we have in yellow, we have our crankshaft sensor, and in green, where you can see it, that's our camshaft sensor. But we see this little nonsense going on right over here. Now, for those of you who haven't scoped a cam and crank sensor before, something ain't right. But those of you who don't, who aren't used to that, let's do a little bit of deductive reasoning and see what's going on over here. But first, what we'll do is we'll talk about how crankshaft reluctor wheels are set up. You generally have, it's a 60 teeth cut out in a ring with 2 missing teeth. It uses those 2 missing teeth to identify that the crankshaft has made 1 full revolution, and the camshaft can pulse up against that, so it knows how to adjust your timing and your fuel injection. Okay, and we're actually looking at that now. This car looks like 2 missing teeth or 2 sections missing. Okay, is that a problem? Well, I don't know. Let's look a little bit further. Okay, so what you can see is right here. Let's look at this spot right there. You see the little whoopsie-doo, and then she climbs back up. Okay, that's kind of weird. But if you look right here, this is kind of sexy, and then it goes right back. Then it goes right back up. I would be willing to bet, if you're new to this, that this is good, this is bad. All right. So now all I want to do is, the only thing that can be, because this repeats, the only thing that this can be is something that moves. It can't be a crank sensor. You could put 50, 60 crank sensors in this. It'll never fire. It'll never want to run. All right. The only thing it could be is something that moves around. So I asked the guy if he can remove the crank sensor. If you got a Borescope, put it in a hole. And he did. And you could see the damage inside the reluctor on this particular crank sensor. Okay, I don't know where this damage came from. The guy doesn't know. He's a 3rd guy in, but now he knows what's wrong with the car. And we're not going to put a computer in the car. We're not going to put a harness in the car. We're not going to put any more crank sensors in the car. This needs this reluctor. Unfortunately for this guy, you got to pull the crank to put this reluctor in because it's physically bolted to the crankshaft. But at least we know what's wrong with the car. And from start to finish, from the support guy, from the guy being called to it, to making a call and going on, I was on the car for less than 15 minutes. And no parts needed here. We know what we need to fix the car. All right, let's move on a little bit. Let's do one more study. We have a 2002 A4 with a 3-liter AVK engine. This engine's kind of special in Volkswagen Audi because it's a timing belt engine. But to do the timing belt on this car, you have to install special tools. There are no timing marks. You have to install special tools on the cams. There's like little cam locks that go up on the top, and then a little pin that nobody ever puts in because you can always make your own mark. But these engines, generally when I get a call for these after they do a timing belt, it's because they didn't use the tools or they tried to make their own marks. This car is a crank no start. Okay, so this car has codes for all 4 cam sensors. This car is a used engine. The customer changed the engine because the drive belt came apart and blew apart into the timing belt, making the timing belt fly apart, and it bent all the valves. So instead of replacing the valves, replacing the heads, they just put a motor in the car. The customer did the right thing. He replaced the timing belt using the proper tools and procedures, and I know he did because I grilled him on how to use it, and he told me exactly how he did it, and it was right. The customer also verified that the engine was the exact same code. And for those Volkswagen Audi guys that are listening, they know how important that could be, because even with the same engine size, if the engine code is slightly different, the timing marks could be slightly different. But we verified everything was the same. The customer even went so far as to change all of the known good working electrical parts from the original engine to the new engine. This car should run. So I want to check the same thing. We have codes for the cam sensors. I'm going to assume that something off with the timing. So we want to check the engine speed sensor, which is a crank sensor, versus cam sensor 1 and 2, and 3 and 4. Okay. This car has 5 things I want to check, but we only have 4 channels on our scope. What do? It's pretty simple. We can split it up into 2 tests. All right. So we can go to bank 1, exhaust cam sensor, intake cam sensor, and the crank sensor. And bank 2, exhaust cam, intake cam, and then the crank, and then save them. Okay. And that's exactly what we did. We captured bank 1. Okay. Got some squiggly lines. Bank 2, we got some stuff. Awesome. We have some squiggly lines. Now what? We need to know what good is. You can't just look at something and see it, and just, you need to be able to compare to get something good. All right. So we need what's called a known good pattern. All right. And there's a lot of places online and with friends, if you have a good network of friends, that have known good patterns. In this case, Diagnostic Network is a great spot for this. We have our hero here, Hans Jorgensen, over in Utah, just kicking ass over there, doing Volkswagen and Audis and Euro vans. Awesome dude. Go find him. He loves it. And he went and uploaded the same exact engine code to Diagnostic Network, and we have our same tests. So we have bank 1 and bank 2 intake, and exhaust. We have everything we need. So we download them, and we look. We have in this case, we're looking at bank 1 intake and exhaust. We got bank 2 intake and exhaust. Okay, so let's go back, and we can see what we're going to do is what we want to reference when we're doing this. For us to count it, we want something easy enough to reference it with. So we're going to reference on the crankshaft sensor the sync notch, and then these leading edges will count the distance from the sync notch from those cam traces. So we have it there, and we have it there. Awesome. So now we got to go back to our suspect vehicle. And if you look, we can see, first of all, that our relationship between cam, if you look here and then look here, it's about the same. Okay. But we do know that that isn't right. You can see it's off versus our known good. You see that? Same thing on this side. So what does this tell us? This tells us that the cams are all retarded from the crankshaft by the same amount. The relationship between the cams is the same from our known good to the vehicle capture. The cam and cam relationship is exactly the same. And we know that the proper tools and procedures were used while timing this engine. So it's fair to assume that the timing belt is not making this engine out of time. So what can this be? The camshaft adjusters can be all off of the same amount, because this has 4 camshaft adjusters, and they can all be off the same exact amount, which, come on, that's not going to happen. The crankshaft sprocket is shifted, or the crank reluctor ring is wrong. Okay, now this is what we have to go back. This is a replacement engine, okay? And the customer did the right thing and replaced all of his parts from his good running, well, it used to be good running engine, to this new engine to assure everything was fine, because he knew that stuff was good. What you can see right here is this particular engine, the crankshaft sensor reluctor ring, is bolted to the flywheel. Now, this flywheel is technically a one-way install flywheel because the bolts are slightly offset. However, if you really want to, you can cock the flywheel a little sideways, get all the bolts started, and just run it home, and it will go in. However, if you look at our missing ring right here, and then right here, it'll go in at the wrong spot. This engine had the flywheel installed wrong. So all he had to do was take the transmission back out, put the flywheel in the right spot, and then go forward. So that fixed the car. So what is a DSO? All right, you guys hear about scopes, you hear about DSOs. A DSO stands for Digital Storage Oscilloscope. All right, not this guy. Some of you guys may have used these. Some of them seen them in the shop. This is just a regular analog oscilloscope. That is not a DSO. All right. So are there different types of scopes? Yes, there are. Most scopes today fall into 2 basic categories. All right, you have your laptop-based or you're all-in-one. Okay. On your laptop base, you have a fully functioning mouse and keyboard. You can use your choice of monitors. They're upgradable individually. If you want to upgrade your scope, you can. If you want to upgrade your computer, you can. And the scope and computer are separate. Okay, so if something happens to one, you're not SOL. You have your all-in-one. They're extremely portable, which means the scope and everything is one there. You just bring that over and hook your wires to it, and you're good. There's less wiring involved. Okay, sometimes it can come with a scan tool in case so you take like the Snap-on Veris. There's actually a scan tool involved in there, so you can go back and forth between your scan tool and scope. Problem is they're not upgradable. So say you want the latest and greatest in technology, you have to buy a whole new platform to get the latest and greatest. And the other thing is if one thing breaks, it's all over. It's broken. You can need something newer. It's got to get sent out for repair. Okay? So one of the next questions I get asked is, what scope is right for me? Okay? My answer is the one that you will use. Okay. I also asked them, do you have one that's currently collecting dust in a toolbox? And a lot of the times you do. All right. I advise you learn how to use that before going any further. Before going any further and spending, $1,000 to $2,000 on a scope, use what you got, max that out, and then you might find it works for you, and then move on. All right. This will cost you nothing but time to learn. All right, but it'll make money if you do learn it, and that's a fact. I showed you 3 cases where fixing a scope saved the day. All right, and I can't stress this enough. Practice on good cars, so you know what good is before getting bad. Okay, so I'm considering purchasing a scope. What do you recommend? Well, funny you should say that. We currently sell the Pico Scope. We have a custom branded, sexy, black cased Pico Scope. It's a 4425. All right, it's got 4 channels. It's got a 200 volt input max, or 2000 volt attenuator. This is important. Okay, you need to know the limits of what your scope can take in. All right, if it's only a 50 volt max input, and you hook this up to an injector that's got flyback voltage over 100 volts, you can easily smoke your scope. You may have to use an attenuator to let it handle the voltage. An attenuator is, excuse me, an attenuator is a little thing you put in line of the scope and it actually lessens the voltage and lets it go in. All right. This particular scope is capable of 4 million samples per second on a single channel. With all 4 channels working, it does 100 million samples per second. You have access to a waveform library. The Pico Waveform Library, if you guys have used it, is actually a really great resource. You set up an account, and as long as you have your scope connected to your computer, you can get captures from all around the world on what it is. It can really pull you out of a jam. It has a fully customizable probe setup. People that are a lot smarter than me, you can set up your own kind of probe with your own math inputs, and you can measure almost exactly what you want. You can measure almost exactly what you'd like. You have easily shareable files. Take into consideration Hans Jorgensen, Hans or Hans. He uploaded his files to Diagnostic Network. It's easy enough. And if I wanted to, I can call him because we're buddies, and I can call him and say, I have this car. Do you have a known good? And if it's a Volkswagen or an Audi, he generally has it, and he sends it right over to me. Half of my training classes that have scope captures in there are due to that guy right there. All right. So how do I download Pico? Well, you go to picoauto.com. You go to downloads. You download the Pico Scope 6 software, or the latest version that's available. And even if you don't have a Pico Scope, you can go download the software and run it in demo mode, which is really great. It gets you used to the Buttonology. Okay. So let's talk about the operating system for a little bit. Generally, it likes Windows 7 through 10. 10 is good. 7 is good. It likes to have 10 for its most recommended thing. For USBs, it'll take USB 1.1 all the way to USB 3. Obviously, USB 3 is going to be the best because it's the best, fastest communication you could have for something like that. Okay, so that is the end of that presentation. So what I'm going to do now is we are going to go back over here. I'm going to stop sharing, and I'm going to look at my ugly mug. And what I want to do is I want to do a little bit of live demo here. So we're going to go over to this computer over here, and I actually have a Pico hooked up. And we actually have to get it running. Let me open up Pico here. Oops. Not this one. Okay, here we go. Let's share the screen. Here we go. Share. Yeah, alrighty. Now, let's turn this back in. We're going to load up and turn our demo board on. Come on. All right. There it goes. Come on. So in the meantime, while this is going, let me answer some questions. So we have, let's go at the top here. Stephen Cook asks, what is the minimal refresh rate you recommend for a lab scope? As much as you can get, honestly. Anything is going to be better than a multimeter. It's really the best you can get. Anything is good to get started. Angel saw sync notch was damaged. Good pick, Angel. Elias says, my only fear of Pico is the attenuator stuff. Not needing one on ATS, I'm worried I'll forget to burn it up on the Pico. Yes, that's something you have to be cognizant of. Pico is kind of forgiving. This particular Pico has a 200 volt input max. Wait for this to go. Let's try it one more time. This Pico has a 200 volt max setting. So I've actually accidentally not had an attenuator on there when I didn't realize I was looking at primary ignition, or primary ignition. And if you catch it quick enough, you should be fine. I didn't say that officially. You got to be careful though. All right, cool. So that's the questions I have for now. Let me go over here to the chat. Do I see anything else going on? Yeah, Tony's right. The Snap-on Varus is a PC-based platform. TeamViewer will allow you to remote in. That's exactly how I remote in. That's exactly what I'm going to do now. So let me just go set up my screen share again. All right, cool. We're up and running. Awesome. Turn these two on. So I'm on a little Snap-on demo board right now, looking at, well, CAN bus, and I wanted to give you a little bit of how this some buttonology and how to set up a lab scope or Pico to begin with. And you can see generally right around this area over here, you're going to see our start and stop screen. You press pause to stop it, or and to start it again. All right, that's where you want to live. Now, a lot of people ask, how do I get a good pattern on an oscilloscope? I set it up and I can't see anything. My advice, with pretty much any scope, is cast a wide net. What do I mean by wide net? Well, basically, put a normal amount of voltage on the screen and just put a lot of time on the screen. You'll be able to see trends, and then you can pick away at it until you get what you want. What do I mean by that? I'll talk about it right now. All right. Generally, for most vehicle systems, they excluding any kind of solenoids or whatever, they generally won't go over operating voltage, 14 volts. So if we put 20 volts on the screen, we're pretty much guaranteed to capture what we want. So we can go over to these menus right here, up in the top, and change our voltage. Okay. Now, what about time? That's a good question too. With Pico, I generally like to live with 1 second per division, and I like to bump up my sample rate to around 4 million samples a second. That's generally where I like to live. Okay, on that particular setup. Now, am I going to see anything from here? No, and I'll show you why. So we can stop the scope and go back. I mean, obviously it's a mess, and we can use our zoom windows to go in and take a peek, and you can zoom in, and we can see what looks like a really messy signal. Will this work for a lot of slower signals, injectors, TPS voltages, mass airflow? Yeah, it'll work just fine. But so for something that's really fast, you need to remember the scope is drawing a lot of dots across the screen. If you put a lot of time on the screen, it's got to spread those dots out. But what we're not doing this to just analyze here. We're trying to cast a wide net. So what we can do is we can see the scope running over here. All right, I see number one that my voltage generally isn't going over 4 volts. You can see it. You know, I'm generally not going over 4 volts over here. All right, so I can change my voltage range. So let's move it down to 10 volts on channel 1, 10 volts on channel 2. Now we have much more on the screen. It's something we could see. But what we're seeing over here is still a lot of nothing. We know that stuff is happening. We just don't know what stuff it is. So that's where we change our time base. All right. So right now we're at 1 second per division. So let's change it. Let's drop that right down in half to 500 milliseconds per division. Cool. We still see stuff going. But let's go in a little bit further. So let's bump it down to, let's say, 50 milliseconds per division. Now we see stuff happening. All right. So this is great if you want to save some data. If you'd like to save some data, you can go here, you can pause, and then you can zoom in. We'll go over here to the windowed zoom button. Just take some nibbles here, zoom in a little more, zoom in a little more. And now you can actually see right now, it's actually, the capture is a lot better than what we had before. Is it still perfect? No, because again, we have a lot of time on the screen. We're looking at something really, really fast. All right, but we have a much better picture. And it's easy enough to go there. If we want to zoom all the way back out, we can go to this 100% guy right here, hit that, and we can run the scope again. Let's say we want to look at something live. Okay, we could totally do that. But especially with something like this is a CAN message, if you zoom in too far, it's just going to zoom, pop. It's going to happen all over. You're never going to see it. You're going to want to set a trigger. All right, a trigger tells the scope when to start drawing a picture. All right, and right now is a perfect time to set a trigger when you have a trend view going across the screen. So we're going to live down here at the Pico Scope. Pico Scope has the trigger menu is generally right over here. Okay, so we're going to go over there and set a trigger. We'll put it on a repeat trigger, channel A, and it's going to be on a rising slope. And we got this little dot right here. We're going to move it on channel A, which is blue. We'll just set it right here. So now the scope will start drawing the pattern when it happens right there. But we want to go and we want to look at this CAN bus live to actually see some data. So let's put a little less time on the screen. Now that we have a trigger set up, a good voltage range, let's start looking at some data live. So let's pop this thing down. We're at 50 milliseconds per division. Let's go down to 1 and see what we see. All right, now we can see one single CAN message. And we see that the CAN message is, you can't really see that over here, so we can see the CAN message is living over here. So what I want to do is we're going to zoom in even more. We're going to move our trigger over to the right of the screen. So when I zoom in, we'll see more of the trigger. Okay, so let's move it down just a little bit to catch a little bit more. And we're at 1 millisecond per division. Let's pop that thing down. Let's drop it down to 100 microseconds per division. All of a sudden, we see a live CAN capture. Let's drop it down even more. Let's drop it down 10 times. All right, now we're way zoomed into that scope, to that capture. All right, let's go up a little bit to 20. Now we're seeing the entire message. All right, on the screen, live being driven, and that's a sexy signal, I would have to say. So If you wanted to, you could pause it down here again. And if you wanted to zoom in more, you could totally zoom in more. You could zoom in all you want until it's all messy and you can't see anything anymore. Now, if you ever get too much or too zoomed in and all of a sudden you can't see anything, you have some options, all right? Your options are generally in this area right over here, okay? You can go back one level, which is like that, or you can just zoom out all the way, and then you never lost, all right? I'm trying to see if there's any questions before I should move on. Nothing really that I would like to actually move on to the next scope because we're at 248. I would actually like to move on to the next scope that we're using. So what I'm going to do is I'm going to get out of this. And I would actually like to show you what it looks like. We do the same thing on a snap-on because I find that very important. So we're going to go over here. Here, I'm going to turn the screen share off. Turn this on. Go over here. Screen share on. Application window. This guy right there. Share. All right. What you guys look at now is a snap-on. Veris. This is a first generation Veris. And I wanted to show this for a reason. A lot of people say that I have a junky tool or I got a Modus and it's 20 years old. I got a Vantage, it's junk. This is a first generation Veris. I mean, this is almost an antique by today's terms, but it's still an amazing, amazing tool. And so we're going to do the same thing that we checked on this other scope. So I'm going to unplug on my demo board. I'm going to unplug the Pico. We're going to check the same can capture with a snap-on. We're going to connect our ground, channel 2, and channel 1. Okay. Let me hide this up here. Alrighty. So we see stuff happening. Okay, we don't know what that is. We're going to live down here. Okay, we're going to expand the menu. We're going to play with some things again with a like I said, we want to cast a wide net, and so we're going to do the same kind of thing. We're going to put a lot of time on the screen. So we have 5 milliseconds. So again, we could change this to what we did before. We got 1 second. Now Snap-on generally reverts to 1 second across the entire screen. So when it says 1 second, that means from here to here is 1 second. That's what it defaults to. You can change that to just like a Pico, to 1 second per division. And same thing with Pico. You can change how it defaults to. So if you're used to using Snap-on and you're used to it being 1 second per the screen, you can still change that. All right, so we're just going to live with this right now. So we're putting 1 second across the screen. We have peak detect on, which I'm going to turn off, because peak detect on a Snap-on scope, what that is that Snap-on bumping up its sample rate to the highest. All right, but we're going to live right here. Now we can see we can't really see much going on. The Snap-on, while being a really great scope, is not as powerful as something like a Pico. So you can see it's doing its best to draw a picture, but it's barely seeing anything. So what we need to do is we need to zoom way in. So let's zoom in a little bit. So let's do it 2 milliseconds across the screen. All right. So now we can see stuff happening, but nothing's really going on. But what I would like to do now is I would like to draw a trigger. So let's draw a trigger on trace 1. Put it on a falling edge. Let's move some stuff around. I'll move this pattern up here. Come on, move for me. There we go. Cool. All right. So now we can see some stuff happening, but we can barely see anything. So let's zoom in a little bit more. So we'll go over here, and let's go into 500 microseconds across the screen. Take a look. Now you can see a can capture. But what you can also see is that you don't see much. It's really small. So let's change our voltage scale. So we're on a 20-volt scale here. So let's go down to 10 volts in this channel. Let's go back. And we want to go to 10 volts on channel 2. Waiting for the end. There we go. Go back out of here. Now you can see a lot more. Now let's see if we can see a little bit more detail live. So we're on 500 microseconds. Let's go down to 200 microseconds. Back. So we can actually see the live can capture right here. You can see it. You got a nice mirrored voltage. Everything's kind of pulling all the way down. Our voltage range looks good. If you look for can, you're looking for a can high 2.5 to 3.5, can low 2.5 to 1.5. That's pretty much what you got going on over here. All right. Now let's go back and review it like we could with a Pico. We'll hit stop. And then we'll go to this magnifying glass. That's how we view the buffer. Wait for the buffer fill. And what this is going to show you is our entire buffer. This is everything the scope captured right here. All right. We're going to go and use this move this dotted line because that's going to be our zoom to line. We'll put it right over where we want to check. We want to check this guy right there. Go back to the magnifying glass and let's zoom into, let's go around 16x. All right, we'll move the magnifying glass again. You can kind of see it. You can see a pattern happen, but you can't see much. Let's go all the way down to 1. When you go all the way down to 1, that is the farthest you can go because that's what you captured it at. The fundamental difference between a snap-on and pretty much anything else is if you want to zoom in to see detail, you actually have to go closer than you would normally look at something, save it, then zoom out. Let me show you what I'm talking about. All right. So let's go back and let's go to live again. Come on. There we go. Wait for it to go live. And this turned off, turn it back on. Beautiful. We're looking at stuff. Cool. So what we need to do is we have to go in further. So I'm going to go in way far. So let's pick our, whoops. Go back out again, over here. All right, let's go right here. So this is 200 microseconds across the entire screen. Let's go and we'll change our time base a little bit. I want to go to 50 microseconds across the screen. Now read our message that we have here. The 50 microsecond sweep is only available for trace 1. You must turn off all of the traces. What we're doing is we're butting to the edge of this particular lab scope. So if we want to go on to look at 50 microseconds across the screen, we're only allowed to be able to do that for 1 trace. Okay, so we don't want to do that. I want to see both traces. So let's go down to 100 microseconds across the screen. All right. So this is the closest we can zoom in with what we have going on. So what we can do is, well, right now the scope is capturing and capturing and capturing. We can press stop. Now we hit the magnifying glass. That's going to load the entire buffer of everything that we captured. Just wait for it. Okay, now this is the entire buffer. Now, as you can see, it's less than what we captured before. All right, that's because the buffer on the scope is only so large. Okay, so it can only capture so much. So this might only actually be a couple milliseconds worth of information. So it was 500, it was 200 milliseconds across the screen. So right now we have 0 to 87,040 micros. I mean, this is how much is being captured across the screen. It's actually not much. So doing something like this, zooming in this far, is not good for looking for an intermittent problem, for looking for any kind of weird dropouts or anything like this. This is when you really want to analyze a signal, or so for something that's happening now. But this is how you have to do it on Snap-on. So again, we'll go and we'll move the little bar over to right there, and then we're going to zoom in. We'll go to zoom in to 16x. You can see we have a pattern over here. Let's move the bar over. Let's go to 4x. And we can see a decent pan pattern, a can pattern. So what we're going to do is we're going to make the screen a little bit larger so we can actually see what's going on. Come on, there you go. All right. So now from here, you can manipulate the pattern. You can see the voltages. If we want to go any further, we can totally go on further. That is a great and sexy pattern, and we can go and take a look. And if we want to go any further, we totally can. If we want to zoom into this section right here, we could zoom in to there, which is the spot we captured it at, and we can actually get in really good and look at our pattern. And if you wanted to measure, we could turn the cursors on. We could show them, and we could actually measure our voltages. If you move, if you pay attention, and come on, follow me. Let's go right there. If we want to go and actually measure our voltages, which you have to do with the cursors on the snap-on, you can actually look at your voltage. We got around 3.2 to 2.4, effectively 3.5 to 2.5, then 1.4 to 2.3, effectively 1.5 to 2.5. Those are good CAN voltages for a demo board. Now, remember, this is just a demo board, and this is great. And that's for a basic introduction, that's how you get a pattern on a snap-on scope. I do want to show you the E-scope. I wanted to show the E-scope on the demo board, but unfortunately it's glitching out on me, so I can't. So I'm going to use this E-scope in demo mode to use it a little bit. So let me turn this on. Stop sharing. And go over here, and I want to turn E-scope on. So let me turn that off. Let me go down over here. Let's get rid of that. Come on. There we go. Turn the E-scope on. What kind of questions do we have here? Dean Busby asked, would you recommend using a Handtech scope as a first-time user scope? Dean, if you have one, yeah. If you're looking to buy one for the price, for an 8-channel scope, for as cheap it is, I forget exactly how much it is, yeah, why not? If you're looking to buy one scope, though, and lay with it and keep it, again, my recommendation is Pico. I honestly, my opinion, that's really all you can really say about it, is that Pico is a much more superior scope. Just so happens my opinion is correct, but it is what it is. So Rick Williams wants to know, can you talk more about the mega sample rate? Mine lives at 1 million samples per second. Rick, sure. It depends how you're doing it. Personally, if I have a good computer, and I would like to look at some good detail, and I know it can handle it, I bump my sample rate up to 4 million samples per second. Some computers can't handle it; they wig out. It all depends what you're looking at. I personally am of the belief that if I'm going to analyze something, I want to analyze it to the best of my ability. Yes, if you're looking at a capture, and if you're looking for something that could possibly be some kind of weird dropout or something like that, I don't want any possibility of missing it. So I bump my sample rate up as much as humanly possible. And somebody wrote up that Justin Miller, go back up. Justin, yeah, Ryan, yes, it's right there. I watched some videos from Justin Miller, and he always recommends to bump the sample rate to the max. Are there any situations that this is not a good idea? Ladies and gentlemen, listen to Justin Miller. That guy is a genius. That is the guy that taught me how to do this. So yes, he is right. That is generally what you want to do. You want to be able to use it as much as you can. If you're going to bust out an expensive piece of equipment, use it. All right. So we're here. We're looking at this is the new E-scope Elite. This is the 4-channel that I'm using. This is actually the newest version of software that they have. That some of my gripes about the old software, they got rid of, and they took care of a lot of it. Unfortunately, my scope kind of went bad today, and I couldn't do anything live. But we're gonna play around in demo mode. All right. So what's cool about the E-scope Elite is you have the ability to have basically 2 scopes in one. All right. And that's their biggest thing. With their dual scope function, you can have one time base up top, one time base on the bottom, which is basically what you're seeing over here. I'm looking at an injector signal flying by on the top screen and just kind of chilling out on we're seeing a trend view on the bottom screen. All right, so you can set that right over here. All right, this is running in what's called strip chart mode. And let me see, because my mouse is kind of off, right over here. You can see that it's running in strip chart mode, okay? And down here, you see your other scope that you can set the different mode on. So what we could change that. If we wanted to make the front a triggered scope or set a trigger, we can. We could set a trigger right on that scope. And we could still run the bottom screen on a strip chart in a different mode. And we can also change our time base if we want. You know, if we want to have these things flying by like this, or if you want to have them, you know, you want to see it at a different time sweep. We'll go with, there you go, 32 milliseconds. Let's go down to 16. Cool. So we got it flying by. What's another thing? Another thing that's kind of cool about the this scope is, some people find it cool. Some people find it kind of a pain. Once I realized how to use it, I kind of like it. You're able to focus on what part of the trace you want to look at. Now, say I want to live. I want to look at the entire. This is an injector pattern, and I want to look at the entire pattern. You can set your scope range of your viewable angle, and you can see our upper range over here, or our ranges are right over here. All right, you see our upper range is around 5 volts, and our negative range is around negative 2 volts. So we could set that, and I want to go. My upper range to be 100 volts, my lower range to be negative 2, or I want to see a little bit under it. I can go negative 5. All right, we can look at the entire pattern if I want. Or if I want to look, if I really want to be focused on this particular control pattern right down here, where the module opens or grounds the actual injector to open it, and I want to look at the voltage drop across that injector, I can focus on that if I want. That's the way I had it before. So I can set my range to be from 5 volts to like negative 2 volts, and it really amplifies. I mean, you're not going to see much here, but it really amplifies whatever you're looking at. It's actually kind of cool. Takes some getting used to, but it does work. But where ATS really comes with their own is their measure and deep record. All right, this is where you can go and take a test drive and look for any kind of intermittent patterns. One thing to note first is the measure and deep record button takes their time bases from your dual scope screen. So if you have too much sweep time across the screen, you're not gonna pick anything up. Let me circle that because you can't really see that with my mouse. If you have too much sweep time across the screen, you're not going to be able to pick that up. So you want to make your sweep time applicable to what you're going to check. So what we could do is we can just start our deep record. And what we're doing is we got everything rolling. We're good. We're just chilling. Everything's awesome. And what it's doing is it's saving everything. All right. When we're done, or what makes this good is you can just let this guy run. All right. You can let this run if you're waiting for a car to screw up or misfire or do something stupid. You can be in the bay. You can be the bay next door or bay right next to it or somewhere else. If you hear the problem, with most scopes, you'd have to run out and press stop and then look for a record. Here, you can just kind of go over in a decent amount of time and just press stop. All right. And then what I like to do is I like to zoom out a little bit so I can see the entire pattern. And actually, Brandon Steckler kind of taught me this little trick. What you want to do is you want to zoom out so you can see. You want to be able to see some stuff around it. And then you can pick your zoom window and just zoom in. You could zoom in over here and just zoom in over here. This gets into another thing I want to talk about with this particular scope. What I want to do right now is I would like to move my little face to the top of the screen, right there. All right. The way Pico Scope sets their scopes up is the way most oscilloscopes default to, where the 0 line is along the same plane. And for the longest time, what you would have to do is you have to process data which you can't see. So let me do another screen share so you can see it. Here, share screen, window, this guy here. Can you see it? No, you can't see it. Stop sharing. It's not letting us do it. So let me go screen share something else. Application window here, share. Okay, it's not going to let me show it, but what it would do is you would go and you hit this process data button over here, and from there, if you wanted to separate these traces, if you wanted to separate this trace from this trace, like I generally like to, if you're looking for a cam crane correlation, if you're looking for a cam crane correlation or something like that, and everything is on top of one another, it's really hard to see it, especially if you got 4 cams and a crank sensor if you're running the 8-channel scope. So you want to separate the traces. The only way you'd have to be able to do it is go and add offsets, where you're basically adding voltage to the signal that you're looking at. So you go and you add your offsets to the voltage, and then you would add your offsets, and it would effectively raise it up. Problem is if you do that a bunch of times, there is no way to keep track of the voltage that's there. So what ATS did is, let me set this back to normal, back to where it was. Beautiful. What ATS did is they made that much easier to do. And you have these little guys right on the side over here. These little arrows and those little lights. Okay? So what you can do now is you can easily just raise your voltage up. You can move this voltage up, you can move this voltage down. If you want the other ones running, you could do that. And say everything gets lost and you get screwed up, you just hit this little guy right here, that little guy right there, then you're good to go. Puts everything back to where you need it to be. It's actually a great little feature with the ATS scope. I'm not going to get too far into this because that would be for the next lab scope webinar. This was basically a buttonology, why you need a lab scope, some basics. If I have something in my hands, how can I get a capture? All right, and it's the same kind of thing. It's just basically cast a wide net, then go on from there. So what I'm going to do now is I am going to stop sharing. I'm going to turn this back on, and I'm going to answer really any questions that you guys have. All right, so let's see what we got here. Mark Toy would like to know, how many pressure transducers are there in the Pico kit? The Pico kit, generally, the basic kit or the master kit that you would get would have no pressure transducers in there. That's an add-on. They do sell a full-on master kit with transducers in there, but that's a different price. You have to call for getting prices on that. Let's see. Let's scroll up a little bit. Mario wants to know, what's the difference between filtering and bit resolution enhancement? Depends on the scope, really, that you're really dealing with, Mario. The Pico uses filtering, almost like as filtering it smooths it out. Bit resolution enhancement, I'm confused about what you're asking. Are you I would actually have to get back to you on that, because I don't know exactly what you're asking on that, because that can go different ways. Mario wants to know, is there equivalent on Pico where you can do deep record aside from trigger? That feature is pretty amazing. Yes, you can do pretty much anything with a Pico, and if you want to get crazy like that, again, that's next webinar. Are there any questions? Any more questions that we would have?
Hey, Chris.
Hey, Eric, what's going on?
Oh, just enjoying the webinar, and I thought, since we had an opportunity, you can. We did tag a couple questions. Looks like Keith DeFazio was jumping in there and helping us tag a couple of those. And so if you want to take an opportunity to scroll through that, I will take an opportunity to do a shameless promotion for the promo that we have running here. So everybody, I want to thank you for coming out, and Chris is going to answer a couple more questions before we end this webinar. So obviously, the question about what scope, if you're looking to purchase a scope, what kind of scope would be preferable? Well, obviously, we see the benefits of a scope that's web enabled. That allows for tech support or your friend to jump in and give assistance. So that's one thing that you may want to look for. If it wasn't a consideration, definitely keep that in mind. Web enabled for sharing and for assistance, for a tech support individual to come in and drive a little bit, or see where you're landing in your diagnosis. The obviously right now, Opus is partnered up with Pico, and I have to say, they used to have a partnership with ATS, and I had an ATS well before that agreement, and that was my scope for over a decade, probably close to two, and very happy with the ATS product, and just now moving over to Pico, and see the benefits of both. It just depends on your style, what you're comfortable with. So Chris is accurate in that statement. Which one should I get? Well, the one that you're going to use. So which one is most comfortable to you? What feels right? If you're using it, that's far more powerful than the one that you're not using. So on that note, just a reminder, we've got 25% off that Pico Scope purchase with purchase of a DrivePro ES, and we're going to be running this promo for, I'm not sure, probably at least a month. This month at least. That's zero down, no payments for 90 days on the DrivePro ES, but you get that discount, 25% off the Pico. If you already have a DrivePro ES, contact your sales guys, see what and you're looking at getting a scope, see what we can do for you on the Pico Scope. Probably not get this promotion without the purchase of the DrivePro, but it's worth checking our prices before going elsewhere. And along those lines, I'm going to go ahead and pass this over to Chris to finish up with a couple of questions. And
I have really one more question that I want to answer because we're running a little late, and this one's really important. I want to touch on it. James Dillon asked, Chris, how much training does it take the average tech to become proficient in scoping? Perhaps one who's migrating from basic multimeter use. That was me. All right. I'm not going to lie. I first picked up a lab scope less than 7 years ago, and I didn't know what I was doing. All right. Around 2014, I decided that shotgunning parts in cars, and I was really good with that shotgun. Shotgunning parts of cars was making me 80% at best. And when I'm spending other people's money, that's not a good way to keep a job. So I decided to make a change. And so what I did is I wanted to learn the best way to do that. And how do you do that? You enroll in training. My best thing I found was I went online and I looked at things. I found Scanner Danner online. All right. And I saw that he's using a Varus. All right. And I realized, oh, I got a Varus at work. I saw he was doing a test. I thought that was awesome. You know what? I'm going to do that same test the next day. And I did, and it changed my life. And I didn't look back from there. I bought a scope. I bought a Modus, a first generation Modus. Still have it. Still my first go-to. And in that scope basically teaches you how to use an oscilloscope, front to back. All right. And I just spent an entire Saturday learning every single test. And I just did it. I stayed late at night, did it. So to answer your question, really, it depends how dedicated you are. And the thing is you need to practice on good before you can go bad. I can't stress that enough. The time to pull out an oscilloscope is not when you have, the time to learn an oscilloscope is not when you have a broken car in front of you. That is not the way to get a pattern, because why am I not getting a pattern? Do I have a broken wire? Is that the problem? Or am I doing something wrong? You need to know what good is before you can know what bad is. So to get proficient, depending on if you study this every night, a month or two, you can get really proficient at setting a scope up. Now, knowing what good is and what bad is, that takes time. And do I know everything that's good and bad? No. And another thing is using an oscilloscope. A lot of it is it's not looking at a pattern and go, oh, that's bad. You want to compare. You want to compare. A lot of I call it one of these things is not like the other. You're always comparing. All right. If you're current ramping in a fuel injector, All right, is that good or bad? Well, if you got a V8, you got seven known goods on that car. You just compare it. It's stuff like that. It's little tricks like that you just pass on and go from there. All right. Trying to look at this, see if there's any more question. That's pretty much it. I mean, it looks like everybody's handling it in the trap. And that's really it. So with that, it's 3:18. We're going to end this, and we're going to say goodnight. Thank you for paying attention. Thank you for coming in. Again, take advantage of that offer that we have. It's really good. And with that, have a good one. Thanks. Bye-bye.